So this exercise, I just a simple highlight. If I have the velocity field as showing as the function showing here, and can we provide the definition for the velocity field? And finally, I will say the velocity field, we call that the steady state, and 1D along the x directions velocity field. OK， 哦，那这个很重要，因为大家每次都会被函数的 x 跟 y confuse， 你就会很兴奋，你只要看到 x 跟 y， 你就很想要说它是二维的。这个就是我们的毛病，就是这样子。所以要特别在意的是，其实是要看 ijk 的 component 来决定它是 1D、2D 还是 3D， 而不是看速度里面的函数的 x 跟 y。Okay, so the next slide I would like to introduce, if I already know the velocity field, how can we determine the stream function? The stream function, the topic I write down here, indicates the stream line. If the stream line is the linear stream line, so I can define the function also the linear functions. So how can we find out the stream functions? If I find out the stream function and I can plot the stream line, but the input, the prior knowledge I need is the velocity field. So if I don't have the velocity field, I cannot plot the stream line. Okay, so some assumptions before I derive the equations. So the stream line, the C in here, the symbol, I call that the stream line. And I only focus on the 2D dimensional problems. So right now, my problem is the 2D velocity field. That indicates the velocity only have the I and the J. The velocity only have the unit factors, the I factor and the J factors. So I define my stream functions is a function of the x and y and t. Because I didn't tell you the function is a steady state. So maybe the function is a function of the time. So that means the C, the stream function will change maybe with the time changes. And some assumption very important, I assume the 2D flow is incompressible flow. That indicates the density didn't change, right? Because incompressible, 不可压缩, so the density didn't change. And I define the U will equal to the stream function change along the y directions. Okay, and the V, also the stream function change along the x direction, but I have additional minus in here. And what is the U? U is the velocity along the x directions. And the V is the velocity along the y direction. Okay? So this is my assumptions, and I define two very important equations in here. The first one is U, and the second one is V. Okay, so you need to remember this is our assumptions for our questions. And the very important equation, I call that the continuity equations. I didn't teach in these chapters and before. So the continuity equation, I will tell you in details on the chapter 5. So the next chapter. But then right now, you only keep in mind the formula for the continuity equations shown in the left. So the left is a continuity equation. As you can see, the first items I show in here is a low change with the time, and plus the differential operators inner dot with the density and the velocity field will equal to 0. And as I say, the two assumptions we have incompressible. That indicates the density didn't change if the location difference, right? So all of the fluid particle with the same density, right? So the differential of the density in here will constant, right? And the constant you can put the parameter outside, okay? And so that means the rho is constant values if the flow is incompressible flow. And the second assumption, I say that the steady flow, that indicates the d rho dt is equal to 0. The physical property didn't change with the time changes. So the differential for time is equal to 0. So I don't have this item. The item in here is equal to 0. So finally, the continuity equation will going down and have a different formula showing here. This is the differential operator inner dot with the velocity field will equal to 0. And then you can expand the inner product. So you know that the du dx plus the dv dy will equal 0, right? Because the inner product with the velocity field equals 0. So it's based on continuity equations. So we know that the du dx plus dv dy is equal to 0. Okay, so we know that two important definitions for the u in here and the v in here. So I just put inside here. So the dx and the u replaced by the stream function dy and plus dy and the v velocity you can replace by the stream function dx. So the inside is the minus the stream function dx and it will equal to 0, right? And you reorganize the equation, you can dx dy minus these 2 times differential stream functions and the dx dy and will equal to 0. Okay, so you see the function showing here that 2 items are the same. So minus will equal to 0, right? So that indicates our stream function satisfy the continuity equations. OK， 那这里就很清楚，因为我们自然的把这些 differential 的 operator 带进去以后，发现最后反而本来就是会等于0啊，所以我们的 stream function 会很自然的就满足连续方程式的这个定义。OK， so I emphasize the purpose for this slide again. If we have the velocity field, how can we figure out the stream function? If we have the stream function and we can plot the stream line. Okay, so our purpose is to find out the stream function and plot the stream line if we have the velocity field. Okay, 所以我们的目标就是，如果你给我速度场的函数，那我能不能决定 stream function 要长怎么样？如果我决定了 stream function， 其实我就可以知道流线要怎么画出来，因为我有那条线的函数。Okay, so the next, because we always know that the definition stream line in the flow field are always tangential to the local velocity vector, right? So if we have the tangent element unit vector dr, r is the unit vector of the distance, right? And we have the unit vector dr. So we know that the velocity field factor if I do the outer product with the unit distance factors should be equal to 0 because the factors velocity are parallel to the distance unit factor, right? So if we do the outer product will equal to 0. So I just compute the outer product in here. So you can rearrange the final answer is the u dy minus the v dx along the k components, okay, will equal to 0. That indicates the inside magnitudes in here also equal to 0. So we can say that the u dy minus v dx always equal to 0. Okay? And then you can reorganize the equation so you know that the u dy will equal to v dx. And you rearrange, and finally you can see that u divided the v is equal to dx dy. It's as same as previous slide I showed the equation. I tell you the spatial gradient will equal to the velocity ratio, right? The spatial gradient will always equal to the velocity ratio. Okay, so again, if we derive the formula, so again we can see also the spatial gradient. Okay, so again you have the spatial gradient is equal to the velocity. You can say the velocity gradient or velocity ratio. Okay, so if you would like to find out the stream functions, and the formula showing here always satisfy. And because you can have the u and you can have the v, because we already know the velocity field. And then how can we determine the stream function? Okay, so this is our purpose. So, and then I just keep the formula in here, and I put because I know that u is equal to the stream function d y, and the v is the minus stream function dx, right? So I just put the u inside in here, and put the v in here. So I can rewrite the equation to be the stream function dy and the dy plus stream function dx and the dx, because there is the minus and the minus again, so become the positive. Okay, become the positive in here. So, and then will equal to 0. So that indicates the stream function differential also equal to 0. So that means if along the stream line, I do the differential of the stream functions will also equal to 0, because the two parallel factor, there is no differential difference. So that means the stream function should be a constant. The stream function should be a constant values. Okay, so the constant can be the constant 1, constant 2, constant 3. We don't know the constant, the true values of the constant in here. We only know the stream function will equal to the constant value. OK， 那我们说到这里，其实你会很 confused， 说那我到底要怎么决定这个 stream function？ OK, so the later we have the exercise. So I already tell you, I already tell you the velocity field in here. So this is our velocity field. Okay, we already know the velocity field, and I can say the velocity in here field is a 2D flow, right? Because we have the I and J. and you focus the u and the v. So we know that the u is equal to 2ak, and the v is equal to minus 2y. Okay, and there is no time variable, so the flow also steady flow, right? Because there is no time variable inside. Okay, so the idea is how can we find out the stream function? How can we find out the stream function? So the stream function is our purpose. It's our purpose for this exercise. So again, I tell you the spatial gradient will equal to the velocity ratio. So I know that if I would like to find out the stream function will satisfy the u divided the v. This is the velocity ratio will equal to the dx dy, right? This is the stream. If the stream function will satisfy the formula shown here, and we know that the u is 2ak, and the y is minus 2y. So we know that the velocity ratio will equal to minus ak divided the y. So I reorganize the equations. So dx dy will equal to the minus ak divided the y. And I put the same parameter together. So dx divided x will equal to the dy divided the y minus, okay? And I can do both side integration operation, right? So I do the both side integrations, and then maybe we have the additional constant we have, right? So I plus the c is the constant value, but I didn't know the true constant in here. So I do the integration. I know that the ln x will equal to the minus ln y and the plus the constant, okay? And then I can say that the ln x plus the ln y is equal to the constant values. And because the plus of the log, so that indicates the log inside that I can product the two variables together and equal to constant value. So finally, I know that the exponential c power constant powers will equal to the xy. And no matter the c constant value is what, I know that this is always equal to the constant. Okay? So in here, the x and y is our stream functions. And the stream function is always equal to constant values. But we don't know how large of the constant value because we will have the several streamline in our velocity field. So the different constant values that indicate a different streamline. And all of the streamline will be parallel each other. Okay? So keep in mind the stream function in here is x product with the y. So we see the next slide, I figure I based on the stream functions. So we have the stream function, and this is the xy functions, but they will equal to different constant values. So here we have the streamline 1, streamline 2, and the streamline 3. Depending on the different constant value, you have a different curve. You will have a different streamline curve, but all of the streamline curve will be parallel each other. Okay, so if that indicates if the xy is equal to 1 or xy is equal to 2, so you can plot the different functions for the different constant, right? X equal 1, xy equal 1, xy equal 2, xy equal 3, they are different lines, but they are parallel each other. Okay, and you can see for each streamline, you can have the local velocity factor. So this is our local velocity factors. And how can we determine the velocity factor in here? Because we know that the u is 2x, right? And the v is minus 2y. So you can, and you actually know the point in here. The point in here, the x is equal to 1. X is equal to 1. And the y maybe is the 5.5. So you can put the x and y parameter into the equation. So you can decide the velocity maybe for the u is 2 meters squared per second. And the v is the minus 11 meters per second, right? So that's why this is the v factor, and this is the x u factor. So that's why the velocity factor shape like these directions. Okay, so you have the velocity field, so you can plot each velocity factors. And all of the velocity factors with the same string function constants, and you can create the line. And you connect all of the point will similar to the string line in the right hand side. Okay, so the idea, if we have the velocity field, and based on the idea for the velocity ratio is always equal to the spatial gradient, and you can derive the string functions, but you don't know the string function equal to the two constant values. So you can change the different constant value, and then you can plot the different string line. You can plot the different string line in here, but all of the string line parallel each other. Okay? 所以我们正常遇到的问题，第一个，如果我们要观察一个流场，我们会想办法决定这个速度场长怎么样子。所以如果我可以知道 u 跟 v 等于多少，那我就可以去计算，除了速度的向量以外，我可以去画出这个流场里面的流线长怎么样。因为流线才是真的是这个流场的观察，你可以完全知道它流动的趋势长怎么样子。就像我们说一台跑车，它的流线长怎么样子，那是气体里面的流线，那我就可以知道它受到的这个风阻的影响。所以流线对于我们来讲，观察一个流体是一个很重要的关键参数，这样子。Okay, so if we have the velocity field and we can define the string line by ourselves, and always the string function equal to constant values. So if we change the constant value, we can define different string line. Okay, and all of the string line, they are parallel. Okay, string line 一定会互相平行。所以大家大概有一个印象。So we have the exercise. We always focus the problem on two-dimensional problems. So this exercise, we move to the three-dimensional problems. So because the problem is three-dimensional, so we have the velocity factor include the u, v, w velocity. The u, v, w velocity. And I actually know the u is equal to 2x, and the v is equal to 2y, and the w is equal to minus 4z. Again, based on this velocity field, we didn't see any variable related to the time. So that means the flow also the steady flow. Okay, so I can only focus the xy plane. So right now I only focus the string function, but looking for the xy plane. So again, I know the velocity ratio will equal to the spatial gradient, right? So again, the same idea. So I can put the number inside in here. So it's equal to the x divided y. And then again, I just put the same parameter together and do the integration for the both side. And then I have the constant value in here. So again, so we know that the ln x will equal to ln y and the plus c. So we know that I can go quickly. So the ln x divided the y will equal to the constant values. So finally, we know that the exponential c power will equal to the xy ratio. But the problem difference, I already fixed the boundary conditions. What are the boundary condition? I already tell you the straight line should be go through the point of the xy is equal to 1, 1, 1. Okay, so right now we only focus on one straight line. Okay, so for this boundary condition, we actually know that if the x and y should be the 1, 1, right? And what's the constant value for the c? What's the constant value for the c? So I put the number inside the equation showing here. And then we know that the e exponential c power is equal to 1. That indicates the constant value should be equal to 0, right? So finally, I know that the x divided y always equal to 1. So actually, the x divided y is our stream function on the xy plane, the 2D plane on the xy. And we didn't know the constant. But because we have the boundary condition, we know that the straight line should be close with the point 1, 1, 1. So I can resolve the c constant value is equal to 0. So finally, I know that the x divided y is equal to 1, showing here. So that indicates the x always equal to y, right? So the straight line on the xy plane always linear, always the linear shape. Because the y is equal to x is a linear line, right? And the slope is 1. Okay, so again, so how about if we change the plane to the z plane, xz plane? So we have another case. We change the xz plane. So again, so we just we have the u and we have the w. So it's equal to dx dz, right? And I put the u is 2x and the w is minus 4z. So I know that here is the minus 2 over 1 x divided the z. Okay? So I just also put the same parameter together. So the left hand side dx divided x and the dz divided the d, but there is the minus 2 over 1. And we do the integration both sides, and we have additional constant value c. Okay? So again, there's a ln x, and there's the minus 2 over 1 ln z, and we have the constant c. And I just move the 2 over 1 to the right hand side. So there is maybe to be the 2x squared, and there's the minus z. And because there's maybe another constant value, I use the c1. And I merge all of the log together. So we have the ln x squared divided multiplied z will equal to c1. So I know that the exponential c1 power is equal to xz x squared multiplied z. So again, what's the boundary condition in here? So we know that we have the x and z is equal to 1 and 1. So should be a c1 will equal to 0 again. So we know that the x squared multiplied z is equal to 1. So finally, I know the string functions along the xz plane will equal to x squared over 1. Okay, so the idea, first, we should know the velocity field first. And then we have the velocity field, so we can define the string function. We have the string function, so the next step we need to know the string function, the constant values. Because we always know that the string function is equal to the constant, but we didn't know the constant, how large it is. But if we have the boundary condition, so we can determine the constant value of the string functions. Okay, so for that case, we will have the boundary condition, so we actually know the constant for the string function. Okay, so this is the problems. So we move to the next. So and then as I mentioned, we have the two approach to describe the flow, and the first one is Lagrange, and the second one is Eulerian. So how different they are? As you can see, the first one Lagrange. What's the Lagrange? Lagrange just pick out the 1 point. Because you pick out the 1 point. So how about the initial point? So you need to find out the initial point. So you have the first one, you have the initial point. So we have the initial point because we need to pick out 1 point. So the initial point, how I can say that the initial, because it's related to the t, the time t0, and the y t0, and the z t0. And if I have the velocity function, velocity as function of the time, like we have the second initial, and the second we need to have the ut function, and the vt function, and the wt function. And then I can predict, you can predict what? The location of the next step. The location of the next time step. So what I can predict? I can predict the location for the t1. So we have the y t1 and the z t1. Okay? So the Lagrange, because I fixed the 1 point and I have the function. What's the function? The velocity function. So maybe 10 seconds pass, so I can predict the location after the 10 seconds. But I need to know the initial, where is my initial point. And I have the velocity functions. And I can predict the T1 time point, the location of the fluid. So this is a Lagrange. So how about Eulerian? The Eulerian, just we don't need we don't need the initial point. We only need the velocity as a function of the spatial locations. And at anywhere locations, I can predict the velocity, how large it is. Okay? So the Eulerian compared to the Lagrange, the significant difference is the Eulerian don't need the initial point. We only need the spatial functions of the velocity. So you just pick this point and I can predict how large the velocity at this point. Okay? Don't need to check every point. So there is one very good exercise to explain how difference between the Lagrange and the Eulerian. So you see, again, the Lagrange, we need the initial point. So if I pick up the initial point at this one, And based on the function, what function we have? I have the velocity function will equal to gt, right? And I have the displacement function equal to 2 over gt squared. So I only have the physical property as a function of the time. And I can predict the location and the velocity. And I start from here, and maybe 1 second later, the point move to here. And I know that it is a 1 second difference. So what's the velocity in here? Based on the equation, I know the velocity is equal to g multiply 1 second, right? And I know that how the distance between the 2 points. I know that 2 over g1 squared. So I know the distance. So if I define the initial point and I have the physical property function related to the time, and I can predict the next step. So this is a Lagrange. But for the Eulerian, we only need to have the velocity functions related to the spatial locations. So actually, based on the energy balance, I know that the potential energy is NGH, right? So I have the NGH, I replace the H to the Z, elevation, height. It's equal to kinematic energy, right? So 2 over 1 mv squared. So I cancel out the mass. So I actually know the velocity will equal to the root of the 2gz, right? So for the Eulerian, we don't need to know the initial points. If you provided the d, maybe d is 2 meters. And based on the function in here, I can predict the velocity at these locations. Okay, so the Eulerian don't need the initial point, but the Lagrange, we know we need the initial point. So the table just summarizes the idea. For the Lagrange, you need to fix the one identity. You need to fix the one identity and to see the path line for this material. But the Eulerian, we don't need to fix. We only need the spatial location informations. And I can predict how fast of the flow velocity. So what are the dependent parameter we need? We need for the Lagrange, we need to initial point, and we need to the physical property as a function of the time. And for the Eulerian, we don't need the initial point. We only need the spatial point informations, and I can predict. So usually, I will say for the fluid mechanism problem, usually we use the Eulerian because the Lagrange is very difficult to apply in real case. Because the Lagrange, we need to fix the one point and to see the point movement when the time changes. But it's very difficult because we cannot capture the one point at the liquid inside. OK， 所以通常我们比较用尤拉法，因为 Lagrange 必须要锁定一个目标，然后你去追踪它。可是你看，你有一杯水，你根本没办法抓住这杯水里面的某一个水滴，所以其实实际上 Lagrange 很难执行。那你为什么有办法抓住水里面的一个水滴呢？你可以撒什么墨水，那你就可以去观察这个墨水随着时间它的移动，那你或许可以抓住这颗水滴，对不对？可是很困难，不是每个环境都可以这样做。所以我们在流体力学的问题里面会比较用尤拉法来描述流场，比较少用 Lagrange 来描述流场的变化。当然你家里有一个喷水池，你把一滴墨水滴下去，你其实可以知道水怎么喷出来的。但是我们实际上野外的状况很难这样做。Okay, so usually for the fluid mechanism, we use the Eulerian approach to describe the flow conditions. Okay, so there are many flow conditions I didn't mention. So the next one is a uniform flow and then non-uniform flow. So if you compare to the steady and the non-steady, how different? The uniform indicates if the physical property didn't change when the location difference. That means the flow is uniform flow. So for our fluid problems, we will say the velocity field didn't change with the different locations. That means the flow is uniform flow. Okay, so you can see the flow, the straight line always horizontal. That indicates if I have the profile in here, the profile along this profile, all of the points with the same velocity, magnitude, and with the same directions. But if not, so here, if not, so you can see some ideas, the convergence flow is not the uniform flow. Or the vortex flow that indicates rotational flow also is not the uniform flow. Okay, and the two important flow conditions, the first one we call that the laminar flow, and the second one is the turbulent flow. So how can we distinguish how different they are? So the nanos, we have the nano numbers. So the nano, the author, we call the nano, define the nano number to distinguish the laminar flow or the turbulent flow. But the significant difference for the laminar and the turbulent flow is dependent on the velocity profile. So you see this is a parabolic profile for the laminar flow, but this is the profile for the turbulent flow. So the turbulent flow always would like to change the parabolic profile to be a uniform flow. So the shape in here for the turbulent flow looks like the uniform flow profile. But in here, not the uniform. Left hand side is not the uniform flow. And there are some oscillations. You can see there are some oscillations. And then we call that the oscillation is the disturbed velocity along the velocity profile. Okay, and usually we call that is ADs, volume, ADs. So until now, there is no certain velocity function can describe the turbulent flow profile. Because you can see the turbulent flow profile, velocity profile have some fluctuation. There is no function can describe the velocity profile. So usually we will calculate the average velocity, and we have the additional U prime. It's disturbed velocities. So the most important, how can we determine the turbulent flow of the velocity magnitude? We will use the average velocity plus the U prime, and the U prime is randomly disturbed velocity magnitude. Okay, so and in that way, usually we call that the turbulent flow is unsteady. Unsteady, that means the flow profile will change with the time. So because the random disturbed velocity will change when the time changes. So usually the turbulent flow, we call that the unsteady. So as I mentioned, the nano authors, he defined the nano numbers. So you can see, I already tell you a nano number if less than 2,100, we call that the flow is laminar flow. But the nano number larger than 4,000, we call that the turbulent flow. And this formula showing here, we can compute the nano number very quickly. And this nano number is especially in the pipe flow. Only satisfied for the pipe flow. 管流，只有在管流里面才适用。And so how the parameter showing here, the low is density. Okay, and what the U in nano number? U is the flow velocity in the pipe. And what the D? D is diameter of the pipe. And the mu is the viscosity, right? Okay, so that's the physical meaning if the viscosity is large. If the viscosity is large. So that indicates the flow. The fluid is very difficult to flow, right? So the nano number will smaller. The nano number will be smaller. If the mu larger, the nano number will small. And then the small will have the nominal flow. And if the speed, the flow speed is too high, and the nano number will increase a lot, the nominal flow will move to the turbulent flow. Okay, so that means the turbulent flow is unstable compared to the nominal flow. 那 nominal flow 中文就叫层流，那 turbulent flow 就叫做问流。问流就是一个比较不稳定的状态。Okay, so it's very idea how can we distinguish the flow conditions. So the final one is the viscous flow and the inviscid flow. So as we say that before, if we call that the viscous flow, that indicates the mu is large. So we have the shear stress in our problems. We have the shear stress in our problem. For the water, the mu is quite smaller. So if our problem is the liquid fluid is the water, so sometimes we neglect the viscosity effect. So we call that is the inviscid flow. That means there is no viscosity effect. So no shear stress inside our problems. Okay. So how many flow we have today? We have the steady, uniform, and nominal, turbulent, and viscous, inviscid today. The flow we have today. So we can describe the different flow conditions that are based on the different definitions. OK， 好，那今天可能就